Algebra 2, here we go. We are starting chapter 7, and 7.1 is exponential models. And then we get into 7.2, they're kind of blended together here. Exponential graphs / properties. Okay, so let's just read here. A population of 12 rabbits doubles every year. Find the population of the rabbits in years 0 through 4. Find the population in the nth year. So that just sort of means in general. Okay, so let's do some exploration here. In year 0, okay, we're starting with 12. So that's our start. So in year 0, we have 12. It says we start with 12, and let's just see how it grows. All right. Well, it also says it doubles every year. So after the first year, we got 24, okay, and then 48, okay, and then we're going to double 48 for 96, and then 192, and then this is just in general. All right. So this is just 12, okay, and this is then 12 times 2 one time. All right, and then this is 12 times 4. Okay, this is 12 times 4. Well, that is 2 squared. That's the same thing as 4. 12 times 4 is the same thing as 12 times 2 to the second. This is 12 times 8. Well, 8 is 2 cubed, so you can see the pattern here. And we could even go back and pick it up right here, 2 to the 0, because 2 to the 0 is 1, and so 12 times 1 would be this 12. All right, and so this one is going to be actually 12, if you were to look at the calculator. This is going to be 12 times 16. Is that 192? Okay, so 12 times 16, and that's to the 4th. So for the nth year, just in general, we could say 2 to the nth. All right, so the expression 12 parentheses 2 to the n is called an exponential expression, okay? And that is because the exponent n is a variable, exponent is a variable, and the base 2 is a fixed number, okay? This is called your multiplier. All right, so if we box this out, y equals a times b to the x, where a is going to be the initial value. So how many rabbits did we start with? B is this multiplier, so doubling. So this initial amount, so this would be a initial. This would be b, the multiplier. All right, and then to determine the multiplier when given an A here to the, let me get my glasses on, that's so tiny I can't even read it. When given an A, when not A like the A in the formula, but like a percentage. Okay, so exponential growth, you're going to take, 100%, and with decay, you're going to take 100%. Okay, so if you have exponential growth, if you're growing 5% a year, you're going to take that percentage and add it. So if you're growing by 5% a year, you'll have the 100 of your original. So if the rabbits are growing, they'll be, as a percentage, keep all of those, keep 100% of those, and then you're going to add in that growth rate. So with exponential growth, you add it in, and then with exponential decay, you're losing part of the 100%, so you subtract. So first thing we're going to do is find multipliers, just a little warm-up activity, find some multipliers. So 7% growth. So as we grow, we're going to be adding on 7%. Which is 107%. But math needs decimals needs percents to be in decimals. So that is 107. 1.5% growth. This is 100 plus 1.5. Okay? 100%. Oh, I don't need to write that 100, so I'm out of room. Plus 1.5. 101.5% or 1.015. All right, so decay, you're going to minus 6%. You're not going to keep 100%. You're going to only have 94%. So 0.94 in the equations that we're going to do. And then this is minus 8.2%. All right, so you're going to be left with 91.8%, which is 0.918. Okay? So this is kind of like when we were doing the sale price of something. If you have a 20% discount, then that's kind of like a decay. You're only paying 80% of the cost. All right, so we're going to go into some calculator activity. Use your calculator to compute to 3 decimal places. If x is 2 over 3 and y is 3.4, 42 times 2 to the x, so that'll be for this one, and then the y for this one. Okay, so 2 different things there. So I'm just going to go and I'm going to punch in 42, and I'm not going to write times 2 here. I'm going to use that parentheses just so it looks like the problem. Oops, it's a good habit. 42 parentheses 2. Okay, so we go up arrow, and then we're putting in x is 2/3, and I want to put 2 over 3 minus 1 in parentheses also. So this is what this would look like in the calculator. 42, 2, and 2/3 minus 1. Okay, so parentheses on the base, up arrow, and then the whole exponent in parentheses there. And this comes out to then 33.335. All right, the next one, 0.8 raised to the 3 times y. So 0.8 raised to the, in parentheses up here, 3 times 3.4. All right, and this will come out to be 0.103. So just practice with the calculator, getting things done, inputted correctly so your output is then correct. Okay, next thing, some applications here. This is all going to be your Math Excel, these applications. So important to read carefully. The initial population of bacteria in a lab test is 400. So that's going to be your A right here. The number of bacteria doubles every year. Okay, so doubles. So if you have here this 1 plus R, okay, this particular equation is if you have a growth rate. And the rate is in decimals. Okay? If you had a decay, you'd have this. Decay. All right? And let's move this. And you always want the rate in decimals. So this is a little misleading for us to have this doubling. This is not an add. This is not an add a percentage. Okay, this is not an add a percentage. This is my new amount in terms of time will be the initial, and this multiplier is 2. It's not 1 plus 5% or anything like that, okay? It is just 2 for that doubling. So be careful. This formula is sort of misleading, I think, as a heading on this note page. And then 3 hours. So you're going to this equation sort of right here, this one. And so I'm just going to add it. Here's some equations for us. 1, 2, and then another one, 3, would just be A of t is that initial times some base to some time. So this would be like if you're doubling or halving or what have you. All right, and so so we'll just do this. So please don't make this 800 raised to the third power. That is not the correct answer. You have to do 400 parentheses 2 cubed. And that is the correct answer, 3,200 bacteria. All right, at the end of 5 hours, so really you're putting in 5, just using our function notation. So this we were putting in 3 into the time. This is an exponential equation because the exponent is a variable. Now we're putting in 5. So you obviously will be using a calculator here. So 400 parentheses 2, 5. So now we're at 12,800 bacteria. Okay, so there is one, and I'm just going to outline the formula that I used for this particular problem. Okay. The initial population of bacteria in a lab test is 400. Okay, great. The number of bacteria doubles every 30 minutes. Okay, so with this one, we just want to keep an eye on our time. It's still doubling. 2 for double. But the end of 3 hours here, this doubling time is 30 minutes. So the amount of time it's going to double in 6 hours, we're going to be using time of 6. 30 minutes does not cooperate with 3 hours. So we'll be using a time of 6. That's just how many increments you have of the doubling. So if we double over 30 in 3 hours, that's 6 increments of the doubling. So this formula, I'm going to use this one also. Use this one here, and it's going to draw my arrow the wrong way. And here. So this will be A of 6 is equal to 400 doubling to the 6. And I'm just, on my TI, I'm just grabbing the entry and putting in 6. So this is 25,600 bacteria. I ran off the page, we'll just put back. Just abbreviate, just ran off the page there. And then at 5 hours, so I'm not going to blindly put 5 in there. If 5 hours, that's going to be 10 30-minute cycles. So we'll change that to 10. I shaded right there. So you get 409, 600 bacteria. All right. So let's box these out and move on to the next one. Okay, so the next piece down here says a certain medicine is eliminated from the bloodstream at a rate of 18%. So when you see the percent, now you're going to be thinking of these two formulas. All right, and so this is decay because a medicine is leaving. So this is going to be 100% minus 18%. Okay, so that's going to be 82%. So our multiplier here is 0.82. All right, so if 60 milligrams of the medications in the bloodstream predict the amount of medicine remaining after 20 minutes. So minutes, those are communicating. And so this formula, I'm going to use A of t equals initial, that'll be my A, initial 1 minus that rate to the t. So this will be A of 20, okay? A of 20 here is going to equal 60, all right? And this is 1 minus r, which is this 1 minus r. Right here's this 1 minus r, but you want it in decimals. Okay, so this is 0.82 to the 20. And that's using this formula. Okay, so 60.82 to the 20. All right, So we are left with 1.134 milligrams left. So we started with 60 milligrams of a medication, and at 20 minutes, you're left with 1.134. All right? Suppose you invest $200 into an account, so that's your beginning, initial. And you earn 6.5, so this is growth. So this one is going to be using this formula. We're going to be growing. All right? So the multiplier here is 100 plus 6.5, so 106.5, so 1.065 in decimals. Okay, so that's your percent, and this is in decimals. Using this, so write an expression that will predict, or even if I'm going to just write the formula. So initial is 200. Here comes 1 plus r, which we've already done up here, to the t. Find the balance after 7 years. 200 parentheses 1.065 to the 7. And we will have 310.80. So our money grew. We kept that times 1 means we keep the 200, but we're growing. 7 years, and it came out to, what did I say, 310.80, and that's money. Okay, when is the balance at least 1,000? Set up an equation. So now this is that we saw in when, and this is really a foreshadowing of what we're going to do in this chapter. When do we get 1,000? So this is what you get, right? And that's that A of something. So when do we get so I'm going to put that where the A of something is. This is the A of some time t that I don't know. When will we arrive at 1,000? If we start at 200 and we get 1.065, okay, and then t. So we're solving for t. How do I solve for t? T is in the exponential position, and this is the big idea of this chapter 7, where we get into exponential equations and then something that's called the logarithm. The logarithm is going to allow us with algebra to get that, pull that t down and solve it. I'm going to show you on a graphing calculator, and in class I would show you on Desmos. I can't really do Desmos here because I'm not on a Google Meet where I can share my screen, but I'm going to show you on a graphing calculator how this would work, and in class I'll show you in Desmos. So the first thing I would do is probably, divide out the 200. So just let's get this out of the way. So let's divide by 200, divide by 200. All right, so I've got 5 equals 1.065 t. Okay, so I'm just going to graph those two. So on a graphing calculator, and we'll show you how to do this on Desmos. I wish I had my other one that didn't have the shadow, but that's okay. Okay, so here we go. I'm going to hit y equals. Okay, so y is, y equals. And I want to do y equal to 5. That's the one side. And then I want to do y equal to 1.065 t. And there's no t on these graphing calculators. You just have to have an x. Same thing on Desmos. So I'm going to graph this, and I just want to see where they equal each other. So where do they intersect? Where do they intersect? All right. So I'm just going to go here and graph. There goes 5. That's y equal to 5. Let's straight line across. That's a constant. Y equal to 5. It's a horizontal line. Okay, now I need this to intersect. Okay, and it didn't. So that just means if I look at my window, this is 10 by, negative 10 to 10, and then negative 10 to 10 scaled by 1. So I need to look further to the right. So I'm going to go here and say, I don't know, let's go to 50. I don't know how long this is going to take. Let's just push this way over and go over to 50. So on your coordinate plane now, you can see I've got 10, 10, 10, and now I'm going over to 50. And so here comes the graph, and now they've intersected. So this is going to be the answer to my question, okay? This is going to be the answer. On Desmos, you'll just kind of and on Math Excel, it has Desmos built in there. So you'll just kind of push your mouse, or you'll just, on your Chromebook, you'll just put your cursor right here and it'll give you the answer, okay? But on this graphing calculator, I have to do an intersect. So I have to calculate something, which is right here. Calculate, intersect, which is 5. And then you just have to push this enter button 3 times. I can't see that, but I'm just going to push this enter button 3 times. Kind of glare there. Okay, so I'm just hitting enter, enter, enter. And it's going to tell me exactly where this is. So it's intersecting at 25.6 years. And that answer was just right down here. You can see that. 25. Y is 5. What's X? 25.6 years. And this will be a little easier to get through in Desmos. All right, so that is page 1. Do one more problem on page 2, and then I have to run up to the office and take a break, but I'll come back. So if I go to this page here, so suppose you invest $100 in an account that earns 5% interest compounded annually once at the end of the year. How much is your investment worth after 12 years? Okay, so this is growth and compounded annually. We're going to talk about compounding in very much in depth down here. But compounded annually, you can still use, there's a more complicated formula for if you don't compound annually. But if it just says annually, that means yearly. You can still use this A of T equals the initial 1 plus the rate T. So compounded just means, well, interest means you're earning money on money. Okay, so interest means you're earning money on money. So you go to the bank and you let them hold your money, and they're going to use that out in the stock market, and they're going to pay you for letting you hold their money. They're going to pay you 5% interest a year. So if it's annual, you don't have to complicate the formula. You can still use the one from the previous page. So the multiplier here is 100 plus 5, or that 1 plus 0.05. So it's that's 105, right? 105%, which is 1.05. So we start with 100, and we've got that 1.05, and 12 years. How much is it worth after 12 years? So before we complicate it, if it's annually, if you get your interest at the end of the year, if the bank's going to pay you, for here would be $5, and they're going to pay you at the end of the year, then you can still use that basic formula. So 100, 1.05 to the 12. Okay? And after 12 years, you'll get about $180, 179.50, 179.59. Okay, and you might be wondering why it's not just $5 every year. It's more than $5 the next year because you're now earning interest on $105. So it's not just a straight even $5 every year. All right, I'm going to take a little break, and I'll be right back.